Oxidation-reduction reactions, also referred to as redox reactions, is a reaction in which electrons are transferred. All single replacement and combustion reactions, as well as many synthesis and decomp reactions, are also referred to as redox reactions. When talking about redox, we're going to refer to oxidation states or oxidation numbers. An oxidation state is simply who the electrons will be closer to in a compound. So if it has a negative oxidation number, then the electrons are closer to that element than the element that has the positive oxidation number. These aren't the same thing as charges. They're related, but they're not the same thing. So some rules for assigning oxidation numbers. First, the oxidation state of an atom in an element or diatomic molecule is going to be 0. So here's some examples that you're going to want to write down. If I just had an element by itself, sodium, or iron, or a diatomic element, notice you don't see any charges on those, so all of those oxidation states would be 0. The oxidation state for a monatomic ion is its charge. So if I had Na plus 1, then it'd have an oxidation number of plus 1. Fe plus 3, it would be a plus 3. So in this case, the charge and the oxidation number are the same thing. But we're going to refer to it again as an oxidation number when we're referring to the electrons being transferred. Oxygen is going to be a -2 in compounds, except in peroxides. In peroxides, it's going to be a -1. Remember, peroxide was O2 with a -2. We'll see an example of that in a few minutes. Hydrogen is going to be a +1 in covalent compounds. The only exception to that is when it's a metal hydride, in which case it'll be a -1. A metal hydride is literally a metal and hydrogen, and that's all. So NaH. So in that case, hydrogen would be a -1. But the majority of the times, hydrogen will be a +1. Fluorine is going to be a -1 in compounds because it's the most electronegative element. And then if you have group 1A, 2A, silver, zinc, cadmium, aluminum, or gallium in a compound, it's going to be the same as its normal charge. So group 1A would be +1, +2, silver would be +1, zinc +2, cadmium +2, and aluminum and gallium would both be +3s. The sum of the oxidation states should equal 0 in a compound, and the sum of the oxidation states will equal the charge if it's an ion. So let's see what those mean. So here we have CO2. For CO2, we only have a rule for oxygen. Oxygen is a -2. Notice I put that on the top. I'm going to multiply what the oxidation number is by how many of that element I have. So -2 times 2 is a -4. It has to add up to 0. So carbon has to be something plus -4 equals 0. So that means carbon must be a +4. I put the individual on top and I put the overall on bottom because the individual are what's going to go on these blanks over here. So carbon is a +4 and oxygen is a -2. A common mistake is people putting oxygen as a -4 because they use the overall. Looking at the next example, I have O and N. Again, I only have a rule for O, so -2 times 3 is a -6. But in this case, it's got to add up to a -1. So I'm going to say that equals -1. So something plus -6 equals a -1. Well, that's a +5. There's only one nitrogen, so that one nitrogen must be a +5. So I've got a +5 for nitrogen and a -2 for oxygen. Let's look at 2 more examples. Out of S and F, I have a rule for F. F's a -1. If I didn't have a rule for either of them, the more electronegative will take the negative charge that it normally has. So -1 times 6 is -6, and again it has to add up to 0. So that means sulfur must be a +6. This one has 3 elements, but it's the same kind of problem. Sodium is group 1A, so I know it's a +1, and I have 2 of them, so that's +2. Oxygen's a -2, so -2 times 2 is -4, and I know it adds up to 0. So that means manganese must be a +2 to add up to 0. And again, there's only 1 manganese, so that takes the +2. So I've got a +1, a +2, and a -2. If I had more than 1 manganese, I would divide the charge out for each of them. All right, go ahead and try these 4 on your own. Restart when these 4 are done. So oxygen was -2 times 2 is -4, so manganese was a +4. The second one, calcium is group 2A, so that's a +2. Oxygen's a -2, so that's -8. So that means carbon must be a +6. But notice I have 2 carbons, so 6 divided by 2, each carbon must be a 3. So I've got a +2, a +3, and a -2. For KMNO4, you should have said K was a +1, O was a -2, which means manganese must be a +7. For the last one down here, O times 5 is -10, so that's a -2, so this is a +10, 10 divided by 2, each nitrogen is a +5. Go ahead and pause the video and try these last 4 on your own. Restart when you're done. So for this one, this is hydrogen peroxide. So that oxygen is a peroxide, but even if you didn't realize that, this isn't a metal hydrogen, so the metal must be the +1. So +1 times 2 is a +2. It has to add up to 0, so this must be a -2. -2 times 2 is a -1. That's how oxygen is a -1 in a peroxide. For the next one, you should have got a -2 and a +4, because -2 is -4. To add up to 0, it must be a +4. We know hydrogen is a +1 and oxygen's a -2. So that means chlorine must be a +1, so it adds up to 0 since we have 1 of everything. And the last one, we know that's a group 1A, so it's a +1. We know oxygen must be a -2. So sulfur must be a +6. When something's being oxidized, that means it's losing electrons. The oxidation state will increase, and when it increases, it becomes more positive. Notice I did not say it becomes positive, I said it becomes more positive. So it may have went from -4 to -3. That would mean it's oxidized because the oxidation state is increasing. And then if it's reduced, it's going to gain electrons. The oxidation state decreases because I'm gaining something negative, so it's becoming more negative. So in this case, maybe it's going from a +1 to a 0. That's becoming more negative. Or if it went from -3 to -4, that's becoming more negative. Go ahead and pause the video, make sure you have those written down, and then restart whenever you're done. Oxidation occurs when reduction occurs. They have to occur at the same time, and you can't have one without the other. Some ways to help you remember that oxidation is loss and reduction is gain is Leo says grr. So Leo says grr. Loss of electrons is oxidation, gain of electrons reduction. So you could write Leo grr and look at your paper and be like, okay, loss of electrons oxidation, gain of electrons reduction. One other thing you may want to add on there is if it's being oxidized, remember more positive, reduction, more negative. Another way that you can remember it is oil rig. These mean the same thing, so either Leo says grr or oil rig. Oil rig is oxidation is loss, reduction is gain. So again, oxidation is lost, so it's becoming more positive. Reduction is gained, more negative. So how you would see that in a problem is you're going to be given a reaction and asked who's oxidized and who's reduced. To be able to answer that, first you've got to figure out the oxidation numbers. So we have an element all by itself. So that means that's oxidation number is 0. Here we have a diatomic, which means it's also 0. Aluminum, we said, is always a +3, and that means that each iodine must be a -1. So we can go Leo says Gur, loss of electrons more positive, gain of electrons more negative. So aluminum became more positive, so aluminum must have been oxidized. And then iodine went from a 0 to a -1, so that means it must have been reduced. Let's look at one more example of that. So here I see iron by itself, so that's a 0, and silver's also a 0. Anytime I see elements by themselves or diatomic, I know it must be a redox reaction because by itself it's a 0. When it's in the compound, it's not a 0. Here we have a polyatomic ion, and if that polyatomic ion is the exact same on both sides, such as NO3 and NO3, that's not going to be the thing that changed because none of the oxidation numbers could have changed if it's the same elements. While if one side was NO3 and the other side was NO2, then likely the N or the O changed at that point. But in this case, I know that my silver and iron are the things that changed because they were 0s and now they're in a compound. So silver's a +1 and iron is a +2. Another thing that I didn't note a second ago is these coefficients are not mattering when it comes to listing out my oxidation numbers. I can ignore those and just look at the compound itself. So iron went from a 0 to a +2, so that was more positive, so it must have been oxidized, which means silver went from a +1 to a 0. Notice it became more negative. So silver in AgNO3 is what was reduced. So only the Ag was reduced, not the entire compound. But the thing oxidized and reduced must be on the reactant side. You look at the product side to see how it changed, but only the reactants are the ones gaining and losing electrons. All right, go ahead and try this top one on your own. Restart once you figured out your oxidation numbers and who's oxidized and reduced. So I know oxygen changed. And then I can refer back to what I know for PBS. I know that sulfur normally is a -2, so lead must be a +2. Over here, oxygen's a -2. So sulfur's a +4, -2, and a +2. So I can see that lead stayed the same. Sulfur went from a -2 to a +4, and oxygen went from a 0 to a -2. So sulfur was oxidized because it became more positive, and oxygen was reduced. I just noticed on your notes that these are reversed on this one as well as on this one. So just make sure that you've written those in the correct blanks and you know who's oxidized and reduced. And then this last one has them in the order that's on the video. But again, make sure that you have the previous answers in the correct spots. All right, go ahead and pause the video and figure out who's oxidized and reduced on this last one. We had just done hydrogen peroxide. We said this was a +1 and this was a -1 because it's a peroxide. O by itself is a 0. Hydrogen is a +1 and oxygen's a -2 in water. So hydrogen, notice, didn't change. We had oxygen go from a -1 to a -2, and it also went from a -1 to a 0. Notice oxygen became more negative. It also became more positive. So O in hydrogen peroxide was oxidized. It was also reduced. This is what we refer to as a disproportional reaction, where the same element is oxidized and reduced. That does occur. In order for it to occur, it would have to be in multiple spots on either the reactants or the products. On the previous example, notice oxygen was in more than one spot in the products, but it was not a disproportional reaction. So not every time it's in more than one spot will it be oxidized and reduced like it was in this problem. When balancing redox reactions, just like when balancing all reactions, you have to pay attention to the charge and the atoms. So in a balanced equation, atoms and charge must be conserved, but you've got to pay extra attention on redox reactions. So if you're given two half reactions, like in this problem, so these reactions are going to get added up, so one of them is oxidation and one of them is reduction. The easiest one to look at would be the bottom one, because notice I have an element by itself, so that's a 0, and here's a +1. So potassium lost an electron. So this is oxidation. Notice the electron is on the product side, because I'm losing it. It's losing or giving up that electron. The electron on the other one is on the reactant side. It's gaining electrons. And if it gains an electron, then it's got to be reduction. So I could list out all of my oxidation numbers, but if I see the electrons on the left of the arrow, then that means it must be reduced, and if they're on the right, it must be oxidation. So my overall balanced equation, before I can write that, notice that my electrons don't equal. The number of electrons that I've lost do not equal the number that I've gained. So since the number of electrons aren't equal, we're going to multiply this bottom reaction by 6. Sometimes you multiply both reactions, sometimes you don't have to multiply either of the reactions. Or in this case, we have to multiply 1. Now I'm going to add them up, and I'm just going to leave off the electrons because I'm going to have electrons on both sides, which means they should cancel out. So that's my overall balanced equation. Notice I have 1 dichromate, 14 hydrogens, 6 potassiums, 6 potassium ions, 2 chromium ions, and 7 waters. My 6 electrons on both sides, technically I had 6 electrons here, and I had 6 electrons over here. Those canceled out because they were on both sides of the equation. So anything that's on both sides of the equation can cancel out. My K's can't because they're different, since one has an oxidation number of 0 and the other's a +1. For how many electrons are transferred, it's the number that we crossed out, which is 6. I've gained 6 and I've lost 6. Okay, there's one more. So go ahead and first label who's oxidation and reduction, and then figure out if you need to multiply either of the reactions to get your overall equation. So looking at my electrons, for that first one, I have electrons on the right, so that must be oxidation. And again, if I forget, I can always look and be like, oh, it went from a +2 to a +3. It's becoming more positive, so it must be losing electrons, which means the other one must be my reduction half reaction. And again, they're half reactions because only half of it is being shown. The overall balanced equation will show oxidation and reduction. My electrons do not equal, so I'm going to need to multiply this top reaction by 5. So I get 5 iron plus 2, 8 hydrogen ions, and 1 permanganate ion. And then on the product side is all of the products. Make sure that you multiply by 5 for that iron ion. So that's my overall balanced equation, and my electrons transferred should just be 5.